Okay, so as a quick reminder, Monday again, we didn't have class. I am going to hold you responsible for the Bertozzi video, though. I'm not going to make it a hard question from it, but I'm going to perhaps ask a question on the final that's going to make sure that you actually watched the video. So if you've watched it, great. If you want to watch it, say, for example, it's enjoyable. So it's, instead of watching Breaking Bad rerun on a Saturday night, just Game of Thrones. It is. She's a great speaker. Again, she's one of my favorites. And there's some interesting chemistry in there too. Again, I think it's a good opportunity for you guys to see, specifically with her, the sort of relationship again between synthetic chemistry and how synthetic chemistry can certainly be used to really tackle fundamental problems in biology. All right, so today we're going to cover lipids. It's a rather short chapter, so what I'll probably do is I'll go through what I have, and then I'll probably throw up a few questions just to sort of give you guys a sense of the types of questions that I'm kind of contemplating for this part of the sort of semester, because I know this is a little bit different. It's not synthesis and reaction, so it might be a little bit difficult to sort of know what to expect. So again, today we're focusing on another class of bioactive molecules. These are lipids. Okay. And when we're talking about lipids, again, these are going to be different. Certainly the sugars, we discussed sugars, those are molecules that were carbohydrates, right? Hydrated carbon, lots of alcohols all over them, water-soluble compounds. When we're talking about lipids, largely what we're talking about is heavy carbon-containing molecules. Various we'll discuss sort of greasy. These are molecules that have, majority of them are carbon-hydrogen. There's not too many heteroatoms on them, but as we'll see there will be some, but the majority of these molecules are often heavily sort of saturated. Okay, and so perhaps one of the simplest groups of these are fatty acids. I guess quiet it down a little bit. So fatty acids, it turns out that the name of a fatty acid sort of implies kind of exactly what it is. Effectively what we're talking about is it's molecules that will largely have two parts to them. And we'll discuss, this is just sort of one of the simplest versions of it, but generally what we're talking about with fatty acids is carboxylic acid, right? And then fat, or grease. And again, we'll refer to these terms as one of these things when sort of names that you guys might be familiar with are suddenly then applied to the actual structures of them. So as organic chemists, we'll often talk about sort of aliphatic, strongly hydrocarbons, molecules without much functionality on them other than hydrogen and carbons. We'll often talk to them as sort of like the grease. I think med chemists, we often say, like, if we are trying to make molecules, say, for example, penetrate the blood-brain barrier, we may add grease to it, or if we're trying to pick up some selectivity, we may add grease, because greasy parts can sometimes bind to molecules and so forth. So again, in order for them to have this activity, certainly if N was 0, right, that would just be acetic acid. It wouldn't necessarily be fatty. So largely what we're talking about is long chains here. And again, how long those can be, I'm not really sure what the sort of limit is before it becomes a greasy side chain, but usually we're talking about chains, for example, somewhere in the order of 10 molecules, or 10 atoms or so. It can be 7, 8, 9, 10. I don't know where the cutoff is in that. But again, we're talking about longer chain molecules. For example, one of the fully saturated versions of these, so if you guys remember, saturation means all hydrocarbons, right? A saturated fatty acid would be something that would be just like I've shown you here. So a molecule such as lauric acid, which has 12 carbons total, right? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, right? So this would be lauric acid. this is just, again, you don't have to know what lauric acid is, but if you happen to have heard of it. We can also have them unsaturated as well. So there can also be unsaturated.
They use lauric acid to create the stuff that they put into shampoo.
I think so, yeah. As we'll get to in a while, certainly, as you guys probably know, fats are. And so we also have unsaturated fats. So again, the unsaturated fats would look something like this, but instead we would have things like double bonds in there, right? So we would have some element of unsaturation. So say, for example, oleic acid. Okay, so this would be oleic acid. And again, this is just sort of two different kinds. So you can have molecules, we'll discuss one later on that has multiple alkenes and so forth, but that would be an example of a sort of unsaturated fat. Now you'll notice the double bond in this, right, is a cis double bond, and one of the things that you guys may hear about, right, in say, for example, when you're shopping for food and stuff like that, you'll see things that'll say like no trans fats, right? And it turns out that trans fats generally aren't natural. They certainly can be, but oftentimes the majority of molecules have these sort of cis double bonds, and that's there for a reason, right? Fats are obviously part of us, right? We need them, they're important, but your body also wants to be able to degrade them and break them down. And so one of the ways you guys heard of metabolism, right? Metabolism is often the feature of sort of oxidizing and degrading molecules so that your body can dispose of it. And so when you have something like a cis double bond that's higher in energy, right, this is a molecule that you could likely oxidize easier such that your body can clear it out. Now if that was, say, for example, a trans double bond, right, your body's not going to be able to oxidize that as easily, right? A trans double bond will be less reactive, right? It's going to be more stable. And so what ends up happening oftentimes, especially with like butters and sprays, right, where they want a slightly different consistency, right? What they'll do for like food processing, right, is that they'll take something like the fat or like the butter, say for example, or something like that, and if they want it to be a slightly different consistency, then what they might actually do is start trying to hydrogenate, right, the double bond. So change the makeup of these, because there's going to be some differences in terms of the properties of them, and when you hydrogenate them, that happens to change some of the properties that apparently are favorable for certain, textures and stuff that people might like. But during that process, when you're doing hydrogenation, things can happen such as isomerization. And so during that processing, what can sometimes happen is something like a trans double bond cis double bond can subsequently become a trans double bond, right? And then once you have these trans double bonds, then it becomes very difficult for your body to sort of dispose of them. So that's one of the big issues with trans double bonds, is that they'll stick around for a while, and it might be difficult to get rid of them. So that's why people don't like to have trans fats, and that's one of the reasons why people advertise no trans fats. Okay, so that's in terms of sort of interesting properties within that extent. Certainly, one of the areas where fatty acids are really important. As was just brought up. What's your name? Shio. So Shio brought up. One second. So Shio brought up sometimes in a sort of shampoo, right? We would bring up lauric acid and laurates in terms of how these can be in shampoo. And the reason, sorry, you just made, so real quick, what is it? So it's an isomerization. So using the same, so it's just a side product, right? They're trying to hydrogenate it to change the consistency of the fat, right? So they process it through, and I don't know exactly, I don't know if they feel like palladium, I don't know exactly the chemistry behind it, but it is sort of hydrogenation, and because of that, there'll be things like side reactions, and certainly one of the things that can happen is you can, under those types of conditions, you can end up isomerizing. So the mechanism of that is important, but they're trying to just reduce it, right? But what can oftentimes happen is that, and again, we're probably not talking about going from this to this, but what we're talking about is a lot of like polyene fats and things like that, so you might not be trying to fully saturate them, but you're just trying to change the consistency by hydrogenating for a little while. All right, so again, at the same extent, along the lines of what Shio was talking about in terms of shampoo, certainly you guys all know that fatty acids are sort of detergents, right? And that they are used to clean things a lot of the times. And many of you guys probably know this, but you know, this is oftentimes where you learn it, at least in the classroom, and that's sort of why fatty acids are sort of detergents and so forth. And so if you look at these molecules, right, and you look at a molecule like this, like we said, we have a sort of a polar group, right, and we also have a non-polar group. Right? And what was brought up in terms of the lorates, obviously this is a carboxylic acid, and I have it shown protonated, but certainly by just having it under slightly basic conditions, right, or even at physiological pH, for example, pH of 7 or so, you're going to be deprotonated. So you might see something like sodium laurate or potassium laurate or something like that, and what that's talking about is the carboxylate, so the O-. And so at that point, it's even more polar, it's even more charged. And so what ends up happening is, you can think about these molecules, we'll often draw them like this. It kind of looks like a sperm, I guess. But this would be sort of the polar head group. And this is the sort of non-polar. And so what would happen with that polar region is that polar region would be very water soluble, right? It's going to be interacting with water. So this would, we could also consider this sort of hydrophilic. Right, and on this side would be very hydrophobic. Okay? And this property is something that, again, you can talk about it in terms of soaps, but it has its way in lots of different things, because what happens is, depending upon the media that you're in with these molecules, they can organize in different ways to create different sort of supramolecular structures, one of which is micelles, right? So in say, for example, water, right, if you're using this for soap, right, what's going to happen is the molecule is going to sort of organize itself, right, in such a way right, where on the outside you have all, right, so, who discovered micelles? Oh, I don't know. I mean, obviously people were using soap long before people knew about micelles, so I don't know.
I think you can do like,
look it up and let me know.
I think like they do research with this and like colloidal fluids.
Sure. So anyway, so what you have, right, as these molecules are sort of organized, right, is that there's this sort of organization, right, and the sort of thing is that if you have, say, for example, water out here, right, these are going to sort of bind to the water, right, and then what happens is all the hydrophobic components end up sort of on the inside, right, and so this would be sort of called a micelle, and they can arrange in a lot of different ways. Certainly micelles are what we can sort of think about when we're thinking about how soap works, right? Because if you are trying to clean yourself off, right? If you've just cooked a steak, or if you're, you know, I don't know, whatever. If you've got grease on your hands and you're trying to clean that off, right? And you just try to wash it out with water, right? The water is just going to slip right off the grease, right? You're not going to, water and oil don't mix. But if you take it and you use soap, right, what's going to happen is all the dirt and grease and grime that's hydrophobic, right, will get encapsulated inside of these, right? And effectively what you'll get is a whole lot of beads, right, which are water soluble, which encapsulate, right, the grease, right? So they'll encapsulate it, and then the water can be used to wash it away. And so this is sort of how soap, right, works. People also use this type of strategy for things like drug delivery. I was actually, when I was doing my postdoc at Yale, I was helping out a friend who was in the chemical engineering or biochemical engineering department. I think that was the department. But one of the things that they were trying to do is develop drug delivery vehicles, right? And so, as we were just talking earlier about metabolism, right? Molecules will be oxidized, and so drugs generally have, most of the drugs that you take like on a daily basis, the reason why you have to take them periodically, right, is because your body will clear them out within a few hours, right? Now, and that's, doctors have problems with that, right? Many of you guys here want to become doctors one day, and so you'll appreciate this, but if your patient, you're struggling to get them to regularly take their meds, right? They, that can cause problems, whether it's antibiotic resistance, for example, or any other thing. And so if you could get somebody to take a drug, say, for example, every week or every month rather than twice a day, there might be more of a chance that they would take their drugs. And so certainly there's benefits to things like that. Yeah.
How does medication, like the same medication last 12 hours, rather than 24 hours?
Just how fast the molecule, how fast your body happens to metabolize that molecule. So just different drugs have different lifetimes. So, and there's probably predictive elements behind that. But anyways, what they can do though is the micelles won't degrade necessarily as easily, and they can stick around in your body for a long time. Like say for example proteins. Proteins don't just degrade. Proteins can have lifetimes. Like if you take monoclonal antibody therapy, you get an injection maybe like once a month, and the molecule sticks around your body for a month. So certain molecules will degrade much slower. Micelles can certainly stick around a lot longer. And so what sometimes people will do is they'll encapsulate drugs in these molecules, have things around them that would, say, for example, degrade more slowly, that they know would degrade more slowly, and that would like slowly release the drug. And so they'll try to develop ways in which you can do sort of slowly releasing mixtures, and that way the person would come in, whether it's an injectable, they would go in once a month, and the doctor would inject them with a drug that would release, or if they would take a pill or something like that, maybe not a pill. But anyway, so that's just sort of one of the directions that people are going in. And the other thing that's cool about that is once you have sort of micelles like this, and this is one of the things that we were working on, or I was helping out with, at least on the synthesis side, is that you could actually, once you have a molecule and once you have a delivery vehicle like this, you can then start to think about things like homing device, like homing beacons on them. So you can like attach antibodies to these, right, that might selectively bind to, say, for example, a cancer cell, right? And so if there's a tumor, right, and you're trying to give, say, for example, a chemotherapeutic agent, you can link to these molecules in addition an antibody, right, covalently, and then it'll go around and it will just stick to, say, for example, the tumor and just slowly release the drug near the site of that tumor. And so there's a lot of cool things that people can do, I think, using this sort of technology, and I thought you guys would find that kind of interesting. Certainly there's a lot of other, and your book will discuss a lot of these as well, but these can form in many different ways. We sometimes talk about like bilayers, right? So depending upon the media, you can organize in different ways, right? Where you might have something like this. And again, you can read about this in your book. This is where you sort of get the lipid bilayers. Right, something like this wouldn't necessarily be circular, but could, say, for example, be part of the membrane and things like that. In addition, you could imagine a circular version of these, right? So in the same way that you would have a ball, if this sort of curls on itself, you can imagine situations where you have sorry, I can't fit enough in here, but hopefully you'll get the gist. All right, hopefully you see the point that I'm trying to make here is that this is folding up into a circle. So that's another way to form. Again, is it really important, the way that these happen. Again, if you want to take like a course on this or read more into it, you can in your book. But the point is that there's many different types of secondary structures that these molecules can generate. Certainly these are important physiologically, and you'll perhaps learn more about them if you take a biochemistry course. All right, so those are fatty acids, and that's all that I wanted to talk about them. Actually, I'm going to jump ahead and talk about another fatty acid. So here's another fatty acid that's very biologically relevant, and that you guys may have heard about without really knowing. Okay, so here's another fatty acid, right? It's an unsaturated fatty acid. It's got basically 4 cis double bonds in it. And this is an acid that has a lot of physiological relevance, and it's called arachidonic acid. Okay? And what arachidonic acid is something that's on a variety of different, it's certainly part of cell membranes and so forth. But the reason why it's physiologically important is that it actually serves as an intermediate towards a variety of cell signaling molecules, many of which you guys have heard of. The class of these molecules are called eicosanoids. Eicosanoids are effectively eicosanoids are basically the family of molecules that are derived from arachidonic acid. And the reason why you guys would have perhaps heard about them is that many of these are involved in inflammation and inflammatory mediated processes. So let me say arachidonic acid over here. And one of the early steps in this process is something called cyclooxygenase. Okay? Cyclooxygenase. And cyclooxygenase, there's a couple different forms of it, and they are very creatively called cyclooxygenase 1 and 2. You guys may have heard them more as COX 1 and 2. And what cyclooxygenase does is it will sort of oxidize and cyclize this molecule to generate a new molecule. So I have a 4 space for this. Peroxide there. Okay. So basically, it oxidizes it, it cyclizes it, and you generate this molecule here. Yeah. Arachidonic acid. Arachidonic acid. So that's just, I just feel like rewriting it again. So arachidonic acid. And you make this molecule, I don't know exactly what the name of this reaction is, but it's an intermediate. So this is an intermediate towards a variety of eicosanoids. Not all the eicosanoids, but at least several of them. Yes? Yes. So during the cyclization, apparently it isomerizes. So again, and in this process, you generate these molecules, and the important component of this is that these can then go on to make several molecules that look something like this. This is just one of the classes. Okay, so you see a lot of structural similarities between these two. Again, we've basically just reduced the peroxide bond there and reduced this peroxide bond here. And what you have is this molecule. This is prostaglandin, just one of them. I think this might be A2 or something like that. Anyways, but the point is that these are molecules called prostaglandin. And again, these are inflammation-mediated molecules. So this is a molecule which, when generated, effectively signals an inflammatory response. So when you generate this molecule, you start to get inflammation. And again, obviously, inflammation has historically been an important part of our immune defense system, but certainly with modern-day medicine, it's become almost more of a menace, right, than it has its benefits, right? And so one of the ways to stop the formation of prostaglandins, thus, is to inhibit this pathway here, right? And so when you take something like ibuprofen, right, ibuprofen is a non-selective COX inhibitor. So if you take ibuprofen, what will happen is you'll block the formation of that molecule there, thus preventing the buildup of molecules like prostaglandins, or at least slowing the amount of them down. So that's one of the reasons why ibuprofen is, say, for example, an anti-inflammatory, right? Whereas something like, say, Tylenol, something is just sort of a painkiller, so it works through a different method, right? So, so this is how the sort of NSAID, they sometimes call them non-steroidal anti-inflammatories, work. Now the issue with sort of just as sort of little background. Certainly, cyclooxygenase has been a huge target for inflammation. Obviously, inflammation, you know, Advil, ibuprofen, right? These are huge. Sorry, not yeah, aspirin. Aspirin. Thank you. Again, these are huge. You know, huge market for these molecules. So, but the issue sometimes with non-selective COX inhibitors is sort of that there are other eicosanoids that are generated that can be pretty useful. Like, trying to think of the name of them. Is it the thromboxanes or something? But there are molecules that are still important, right? So if you're disrupting this pathway, you're likely not only disrupting the formation of bad molecules, but you might also be disrupting other molecules. Again, our system is a very there's a lot going on, right? And so it's very complex. And so if you're stopping the formation of this, you're probably also stopping the formation of other things. And so one of the sort of things that people have tried to do is identify, I can't remember which one, if it's COX-1 or COX-2, but there was an attempt, I think it's COX-2 selective inhibitors, but I'm not quite sure. But basically they were just trying to get selective inhibition of one of these sort of enzymes, right? Instead of just inhibiting both of them, could we inhibit one of them? And so this is like Celebrex, Vioxx, were drugs that were on the market to do this, and I believe Vioxx was taken off the market because of issues associated with it. So anyways, when you start to perturb the system, bad things can happen. When I was a graduate student, I'll do a retrosynthesis arrow here. I was actually working on a project related to the arachidonic acid cascade process. And what's important to recognize is that arachidonic acid often comes through from hydrolysis of phospholipids. And so this is another class, sort of introduce you to another class. If you guys have heard of phospholipids, oftentimes what we're talking about is molecules that look something like this. I'll just say R1, R2, right? And so what you can see is that in a phospholipid, right, so this is a phospholipid. Okay, and again, you see those same properties that we talked about previously with, say, with fatty acids, right? We have a charged component to it here, right? And then what happens down here is that these R groups are really long fatty groups, right? And so again, they're important in cell membranes and things like that, so they have very important physiological functions. It turns out that arachidonic acid, one of the ways that where arachidonic acid comes from is hydrolysis of this position here. So this is called the A2 position, okay? And if you can hydrolyze that position, that's how you generate arachidonic acid. And the enzyme that does that is called phospholipase A2. And there's a variety among this class. Basically what this means is it hydrolyzes phospholipids at the A2 position. And so this is how arachidonic acid is actually generated. And so when I was in graduate school, it was kind of neat because I was working on sort of asking the question, could phospholipase A2 inhibition, right, be a potential new and novel anti-inflammatory technique, right? If we could, the problem with, say, for example, COX-1 and COX-2 inhibitors, right, is that if you inhibit, right, the formation of these molecules, what's going to happen is you're just going to get a buildup of this molecule, and something's going to have to happen with it. And so by inhibiting this pathway, you effectively upregulate, kind of, right, the formation of other molecules. So the molecules have to go somewhere. So say, for example, leukotrienes or thromboxanes that might be made through other pathways you might get more of, and they might cause other problems, like I think heart problems, I think was one of the issues associated with Vioxx. And so one of the ideas was, can we inhibit the formation or restrict the formation of arachidonic acid, right? And what kind of impact would that have? And so if we can inhibit phospholipase A2, we cut it off at this stage of the inflammation process.
Also, like that phospholipid is the precursor to.
Yes. So this is the precursor to arachidonic acid. There's lots of different phospholipids. Some of them have this group, right, as this group here. So this will hydrolyze with phospholipase A2. You'll generate this. And so, I don't know. So I did some synthetic work. The molecule that we were working on was kind of similar structurally, at least if you looked at it. It had a fatty side chain to it and had a polar head group, yeah.
Sorry, my question, you said that it's not like A2 or you cut off?
A2 is just the position. A2 is the position.
Okay, so what I'm saying is that would it make the entire molecule just from the position, or it's actually including that phospholipids?
No. So everything else,
Does it like dissociate?
well, yeah, so you hydrolyze this. So this would be an OH, and this would be an OH, so it hydrolyzed. This component here, I forget exactly, but this component of it is also responsible for inflammation as well. It's called something alpha kappa. I forget, but yeah, the other components are also important. You could sort of cut off the development and the generation of those as well. But anyway, so that was the idea. And it was interesting, again, because there's no drugs on the market, unless one has come around in like the last year. I haven't had a chance to look, but at least certainly when I was there, and this was I think a year ago when I last looked into this, there were no drugs that targeted this. But what was cool is because I was sort of reading up on the literature and stuff like that, I got to sort of read about the sort of development of this therapeutic. And so there was a drug called Varisblativ that was being developed that inhibited this, that was very potent at doing so. They were studying it for arthritis, and so they had some pretty exciting data about it. I think it went to like phase 3 clinical trials or phase 2C, like well into phase 2 or something like that. But again, yeah, it's not on the market yet though, but it was kind of cool to see that. And again, this just sort of shows, so, you know, again, many of you guys are interested in therapeutics, and so this is just sort of a story at the molecular level where you can start to think about how drug development, new drugs are put into being, and how sort of drugs that you know about actually function. Okay? All right, so okay.
Arachidonic acid fall under that?
Hmm?
Does arachidonic acid actually fall under that?
Oh, I don't know what the three-dimensional structure is of it. I'm not sure. Probably not. That's probably just the most efficient way to fit it onto a piece of paper, but I'm not sure. All right, so we'll talk about one more class. Actually, we've got two more classes to talk about. I'll start with all right, so the last class of molecules, these are basically fatty, this is really focused on fatty acids, so molecules that are long, side chains. And we're going to talk about one more class of sort of lipid-like molecules, and these are going to be terpenes. Okay. So anyway, so terpenes are molecules. They're certainly found widely in literature. I want to give you a specific example. Pinene, for example, is one. Let's see if I can find a specific structure. Hey, apparently it's not in your book, but I think it's something like this. Somebody want to Google pinene for me? Pinene. I just want to give you guys a simple example of a terpene, and unfortunately it looks like I don't have it drawn. It's something like this. Can I see it one more time? So this is pinene. That's not pinene. I'm just going to erase it and start over. I was a lot further off than I thought I was. So this is one that you guys have probably heard of. This is pinene. Okay. So this is an example of this is a fairly simple terpene molecule called pinene. Again, as you might imagine, this is found in pine, right? So there's a scent of this that's pine. And what you notice about pinene, right, and it's one of the things that you'll see in a variety of different terpenes that we'll discuss, is the number of carbons. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. This is a 10-carbon molecule, and this is one of the things about terpenes. The terpenes generally have some integer of 5 carbons. So terpenes will have either 5, 10, 15, 20, 25, 30, and the sort of nomenclature to them, pinene, and I don't understand exactly why this is the case, but the sort of nomenclature is like every 10 they consider like a terpene. So sort of like 10 is a monoterpene, 20 is a diterpene, 30 carbons is a triterpene, and then like I think 15 is a sesquiterpene. So there's ones in between that have funny names, but they're all sort of part of the same class of molecules. Now, I'll get back to pinene in a second to sort of illustrate something, and at least one of the things that can help you identify whether or not a molecule is a terpene or not. And it has to do with the biosynthesis of these molecules. So terpene biosynthesis, effectively what happens is, again, this early part doesn't really matter, but they come from these acyl groups, coenzyme A, and so this isn't really all that important, but what happens is you make this sort of isopropanol, I think it's called a diphosphate. So it's basically got what's known as an isoprene group here. Okay, so that's a 5-carbon unit, right? And so these are the building blocks of terpene biosynthesis. Sorry, these are the building blocks of a lot of the different terpenes. Let me just draw this out for you. So it's I guess it should be, maybe over 2 minus 3 minus, that would make more sense. So again, this is the sort of molecule, and formally the chemistry that we're going to do on this is that I'm going to show you guys in terms of how these build up on one another is very similar to what you guys have seen in the past. Okay, this group here is basically one of nature's, this phosphate here is basically one of nature's leaving groups. We can sort of think about it that way. And so you can effectively lose this series. You can generate this sort of diphosphate. This is going to be stabilized. And meanwhile, again, this isn't synthetic chemistry. This is biochemistry, so it's enzymes that generally carry out this process. What's going to happen is, I'm just going to put OPT there. What's going to happen is, you are going to, and this double bond can be in multiple different positions, that's just one of them. What's going to happen is we are going to, and we've seen this in the past, alkenes serving as nucleophiles, and the alkene you can sort of imagine is going to react, right, and displace the phosphate. So the so I'll make that the bond. Okay, so this is where I'm making the bond, right? So we're going to make this bond here. So 1, 2, 3, 4. 1, 2, 3. 1, 2, 3, 4. 1, 2, 3, 4. We're going to make a bond to this carbon here, right? And then what we're going to have is, make sure I got this. I use numbers to make sure. 1, 2, 3, 4. 1, 2, 3, 4. 5, 6, 7, 8. 5, 6, 7, 8. So the methyl group's going to be there at the 6th position. That's going to be this one here. And when it reacts, right, what's going to happen, right, is that what's going to be left behind, right, is going to be a carbocation, right, at that 6th position, which then what can subsequently happen, right, is that you can eliminate, put another double bond there, a new molecule can come in, displace it, and what can happen is you can begin to build these molecules up, right? And what happens is at the end of the day, you get to a molecule, in this case, let's say, for example, if I just do the elimination, again, the double bond can go in a couple different ways. I'll just show it when we're substituted. You'll get a molecule that looks like something like this, and then what will often happen is processes will happen whereby something like the oxygen will leave, generating, say, for example, a cationic intermediate, which will then undergo a usually enzyme-mediated, right? It's sort of restricting it within an enzyme pocket, and we'll get it to sort of form molecules, say something like this molecule here, okay? And so this is how they're sort of built up. Now, one of the interesting things about terpenes is that sometimes you can actually see the sort of isoprene unit, right? So this is an isoprene. you can actually identify the isoprene unit within the molecule. Yeah. From here? Well, it can go in multiple different ways. That's just an elimination. I've just eliminated. So and again, as you sort of build up, usually it'll, if there is control over it could be enzymatic, that we put it in the appropriate place. And we'll talk about one in specific, squalene, that's sort of involved in steroidal cascades in a moment. But I want to talk about how you can often identify, say, for example, a terpene, right? And again, these double bonds can be in different places. I just happen to show it in the way that it works there. But what you can often do is sometimes you can actually map out the isoprene units within this group. And so this is one of the questions that I sometimes like to ask, and maybe we'll do some of these later on. We can go through it here, is can you identify the isoprene units in the sort of molecule? And if you notice, it's sort of a head to tail, right? It's the methyl group. This is often the way that it works, is that it's very often sort of where you have the repeating unit, right, where 5 is basically like here, right? You don't have the methyl group here like I accidentally initially drew it, right? The methyl group is going to be here. So there's a symmetry that it'll continue, right, in that fashion. So what that means is sometimes you can identify it or predict, say, for example, how these work. In this case, we have 2 methyl groups here, right? And so we can begin to start thinking about where the other 2 carbons are. Right? And you can sort of see that maybe that's an isoprene unit right there, right? 1, 2, 3, 4, 5, right? And then what you can see is over here, you get that other 5 unit carbon, right? So whether this is the exact one, this is just sort of the one that I identified. But again, you notice that sort of, I'm not saying that that's exactly the one that's formed, say for example in the synthesis of it, so you can sort of see how the tail end, right, the component that's over here is here, right? This is the isopropyl, this is the sort of isopropyl part over here, right? And this is the sort of methyl component over here, right? You can see that this is now bound to the isopropyl component here, right? So you can often identify those isoprene units within molecules. Now, this isn't always the case that you're going to be able to identify these. So if you see, for example, a terpene, or you see a molecule that has, say, 10 or 15 carbons, and sometimes actually, again, you can sort of see them and maybe you won't find them because perhaps there's a rearrangement, right? And to the same extent, but usually that's a good indicator, right? If you have 10, 15, 20, that's a good indicator. But again, that's just sort of one possibility. You could imagine that there could be modifications to the molecule later on that, say, for example, drive a decarboxylation or something, right? And so maybe the molecule have 14 carbons instead, yet it'll be derived from a terpene. But again, at least an initial first hint to know whether the molecule is a terpene or not can often be, does it have 5, 10, 15, 20? And then furthermore, oftentimes, you can actually sort of find those terpene units within there. And this, for synthetic chemists, was historically and still remains something that's kind of, something that people always sort of ask. I remember, again, when I was in graduate school, people would always say, what's the biosynthesis of this molecule that you're working on? Because perhaps the biosynthesis could inspire how you might construct the molecule. Okay? So these are just sort of general terpenes. Again, we'll discuss later on, but one of the questions I'll often ask is this molecule a terpene? And so just, does it have 5, 10, 15, 20 carbons? Furthermore, I could ask you to identify the isoprene units in there. And so those are questions that I think you may want to expect. Okay. So the final molecule in sort of a class of terpenes, in a way, are steroids, which are obviously also very important biological molecules. I'll show you an example of a steroid. Again, that dot is a proton coming towards you guys, just to remind you. Okay. This is testosterone. Okay, and obviously it's an important biological enzyme. And again, what you notice within it that's sort of the core of any steroid, so one of the ways that you will often identify a steroid right away is in particular this sort of 6-6-6-5 ring structure. So this is sort of a hallmark of steroids, right? There's a big class of steroids, right? Estrogen's another one. But again, what you're generally going to see for a steroid is the basic structure that is that 6-6-6-5 ring structure. It's always going to be sort of set up like that, where you have this sort of decalin, right, and then you have the 6-member ring up here with the 5-member ring there. And so this is the general structure that you see within many different steroids. Now, what you notice about a steroid, and I'll sort of explain this in a moment, is that you start to think about these molecules as chairs. Obviously, they're three-dimensional. So you can have sort of a series of the 5-member ring out there. I'm trying to draw in kind of an envelope conformation to it. But obviously, there's double bonds and stuff in there that's going to change the conformation. But at least in the fully saturated form, you can sort of see that it's sort of a series of trans double bonds. Again, we're going to have a double bond here, so it's not going to necessarily be exactly that. But this sort of chair, specifically those 3 chairs, are one of the things that I've often thought is sort of fun to sort of think about, perhaps challenging to think about from a synthetic chemistry standpoint, but certainly reinforcing the idea of chair conformations, and showing how this sort of complex molecule, you see here, can actually be made through a sort of cationic cascade process, which we can envision through these sort of chair conformations. And so, as it turns out, steroids are terpene-based, and they generally come from a triterpene called squalene. Okay? And so squalene I'm still going to run out of space here. All right, well, you guys see this stuff. Okay, so squalene. So you see, squalene is interesting because it's sort of, what do you call this? It's sort of C2 symmetric is what they sometimes call it. Because on this side, you have the methyl group on the left-hand side of the double bond, right? You see methyl group left side, methyl group left side, methyl group left side. But what happens is that halfway through it actually switches, and the methyl group ends up on the right side of the double bond. Okay, and so again, we can map out within the structure all the different terpenes. So this is squalene, right? So you can see the 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. So again, that isoprene unit, you can find them in there. Sort of same time, I'm kind of double checking. Now again, now we've sort of switched over. Now the isoprene group is going to be on the right-hand side. It's going to continue in that way. So again, this is squalene, and squalene is the building block for all steroids. Okay. And I think one of the things that's interesting about this is how, we talked a little bit earlier about how, say for example, when you generate these molecules, there can sort of be built with cation character, which can mediate sort of bond reorganizations and so forth. And in the case of the steroids, as you sort of look at this three-dimensional structure that I've shown over here, don't you know what I kind of drew the enantiomer, but all right, we'll go with what I have drawn so I don't screw it up, because this is very, very difficult to draw. But what you can see in this case is if I start to fold this up, forward. And over here is going to change up a little bit. So the 5-member ring part doesn't really matter, but what you can sort of see, at least in here, is 1, 2, 3, 4, 5, 6. Okay, so that's one chair. Right? And then you see 1, 2, 3, 4, 5, 6. So there's another chair, right? And then here's our other chair over here, right? So what you can see within here is a series of chair conformations, right? And they can sort of adopt this conformation. Again, I'm not going to ask you guys to sort of I don't think I'm going to ask you guys to draw this. If I do, I'll make it a little bit easier. I'm not going to ask you to draw the whole thing, but certainly say, for example, a single cascade process you might be able to do. Because what happens is, and I won't go drawing the whole thing, I'll just sort of show the first 6-member ring formation, and you guys will hopefully then be able to see, at least in principle, how a new cation is formed, which can then react again, which forms a new cation. So I'll show you the first iteration. And then, again, if you guys want, you can try to figure out the rest on your own. But what happens in this process is that this double bond here is going to react with something, right? Oxidation or something like that. Sometimes you can imagine an epoxide. For the sake of just sort of keeping the board space, I'll just sort of draw a proton there, okay? So what I'm doing is I'm going to protonate this molecule, and I'm just going to draw up to that point, and then I'll show the R group just to sort of save time and board space. I'll just draw that R group there. So again, we protonated at that carbon, and what's left behind now, right, is a carbocation, right? Now that we've got the carbocation there, what can happen is this bond can form. I draw in blue. This is the bond that's forming right there that I've shown in blue, right? Right, and then we're going to have that R group there. Now, if I continue drawing that R group, right, what you'll see, maybe I'll just draw it out so you can sort of see. Right, so I just drew the remaining part of that. Now, as you can imagine, now this can form a new bond here, leaving behind a cation here, which is subsequently trapped by the other one. So you can sort of see that in this process, what happens is you sort of generate a carbocation based upon how squalene looks, and based upon the fact that you can sort of adopt into this, again, shared conformation that we've seen in the past, you can sort of see how this can happen. And again, it gets a little bit confusing with that last 5-membered ring because that was a little bit more difficult. In fact, a lot of the people that back in like the 60s and 70s, W.S. Johnson, for example, one of these people basically found how you could imagine promoting the whole cascade and actually get the 5-member ring as well. So this was a big driving force. I still think it's like really cool chemistry, and certainly this is the type of biological chemistry that can sometimes inspire sort of synthetic chemists. Okay? All right, so that is all that I wanted to talk to you guys about today for lipids, and I think that's pretty much it for what I'm going to hold you guys responsible for. With the last probably 10 minutes or so, 12 minutes or so that we have to class, I guess I can start by raising questions, and then I may just throw a couple problems on the board to sort of give you guys a sense of, again, I've told you guys, I want you to just sort of, as much as you can enjoy, right, organic chemistry, this is sort of more trying to culture you guys and just show you guys a little bit of the chemistry, and that may be, well, I don't know what to study, so I'll try to throw up some problems. And again, there is a worksheet that'll at least get your mind thinking. I was looking over the worksheet. It's some pretty challenging problems, but at least get your mind thinking in the way you know, that I'm sort of interested in having you guys think about a lot of this stuff. But so anyways, are there any questions? So the 5, it's again, it's this whole process usually takes place within like an enzyme binding pocket, right? So it's organized in that way. And so the last one is probably just one where, you know, instead of this carbon-carbon bond being made, it's this carbon-carbon bond being made. And so it just positions it in the way that attacks. And again, this was one of the early challenges with this chemistry, and one of W.S. Johnson, who was one of the early people working in this area, what he found is that if you put like an alkyne out there instead of an alkene, you can actually coax it to make the 5-membered ring during the cascade process. So it would be able to be like 666 fire if there was an alkyne out there. So, but in a normal, if we tried to do this in the lab, we would just get 6666. So, all right. So, one of the questions I'll often throw up here, and I may have had this on a worksheet as well, so I apologize if I did. Actually, I think I put it on an exam. So. But sort of, I think terpene, identifying whether a molecule is a terpene or not, can sort of be interesting. These are obviously molecules that our group is working on, called alpha hydroxytropolone. And what's interesting about them is there's not that many of these in the literature. In terms of natural products, there's maybe about, I think there's 4 main ones. There's a couple others that show up every once in a while, but there's been 4 that have been studied, and then a couple others that aren't of as much interest. So these are like the 4 main natural products of this class. And I like using this as an example again because it's chemistry that certainly my group is interested in. But I think it certainly serves as a point of identifying biomolecules and sort of thinking about where they come from. Now, when you look at all 4 of these molecules, they're certainly all in the same kind of compound class, right? They all have that tropanoid, which you guys all know at this point it's aromatic, right? And they all sort of have at least three contiguous oxygen atoms. This one happens to have a 4th. But again, if you were to otherwise look at these molecules, you might assume that they are all sort of related in some way, and perhaps they all come through similar biosynthetic pathways. But if I were to ask you of these four molecules, which ones might be terpenes, which ones would you think would be terpenes? And again, don't say it out loud, just sort of, everybody, this would be the type of question that you might get. Here's four molecules, circle the ones that you think are terpenes and why. I'll give you guys a couple seconds to sort of, a little bit of time to think about that. So let's start with this one over here. Is this a terpene? How many carbons does it have? 10 carbons. Now again, this is an instance where it has 10 carbons. It might be difficult to identify the isoprene units in there, right? In fact, you wouldn't be able to. Well, you could perhaps imagine where they would come from, but likely at some point during this synthesis, it has 10 carbons, and maybe at some point during this synthesis, maybe it started as a, say, 6-membered ring, and then did a ring expansion, right? Where you got an alkyl migration, right? So that it might not necessarily be there. But this has 10 carbons. It comes from the red cedar tree, which is where a lot of terpenes come from. They come from trees, like pine needles. And so, again, it's not known at this point what the biosynthetic pathway of this molecule is, but this is almost certainly a terpene natural product. How about this one? How many carbons does it have? 15. Again, this one comes from, I forget what the plant is, but this one comes from a bush. So this is again, likely a terpene. It's got the 15 carbons. Again, I'm not sure if we can identify. Probably not. I would imagine that these two probably come from a similar biosynthetic pathway. Again, can we find the terpene that's in there? Probably not. I haven't tried. I would imagine that you can't, though. Yeah, you wouldn't be able to. Yeah, let's see if we can do it. I don't think that you can. Which way do we want to go?
Left.
Left. Oh, maybe we can do it. Wait, no.
Just find that intersection.
Go right. Yeah, then you have the linear one. I think it's difficult to find, because again, this one probably stems from a, probably built up, and then maybe there was an alkyl migration or something. So, but again, it's not known what the biosynthesis of this is. My guess would be that they probably come through a similar rearrangement maybe within the synthesis of it. They certainly probably both come from isoprene type chemistry. How about this one? No, right? This one has 8 carbons to it, and then this one, no, this one has 9 carbons to it. These come from plants and trees. These come from, I think, yeast, right? So they actually come from completely different organisms. And so I like this because the biosynthesis of these molecules is known. Should have looked it up before I came down here. I believe it's like catechol-based. So catechol is a phenyl group with like 2 hydroxyls on it. But again, the biosynthesis of this one is known. It's not terpene-based. It comes from a yeast. So it's just something to keep in mind, right? Even molecules that might be of similar classes, right? They can come from they can be different types of natural products. So what they start from can be a little bit different. So again, I think this might be like, there's a class that we haven't discussed. It's called polyketides. This might be one of them. I forget. So, but again, I just think that that's a good example. And again, it's related to research in my group. Any other questions? Yes, Linda. Just practice. It's a puzzle. If you can't find them in there, you can't find them there. So the idea is, you know what the isoprene looks like, right? So what you just try to do is map out the isoprenes in there. And so the challenge about these ones, right, is as you start to map them out, right, you get to a point where you just get this linear one. You don't have that branch point. Doesn't mean that it's not an isoprene. It just likely means, again, you can look at lots of different steroids. I think maybe even the one that I think even testosterone, for example, if you try to map out the squalene backbone in there, at some point there's an alkyl migration. So once you get that alkyl migration, you can at that point no longer identify the terpene units. So just try it on things like, I think menthol, for example, if you just sort of search terpenes, then they might not have them. You might not be able to find them, but just try to identify as many as you can in there. So, all right, yeah.